Welcome to the 21st lecture. We are studying electronic devices and circuits. In our last lecture, we started studying JFETs, junction field effect transistors. In today's lecture, we will study about the output characteristics of JFETs and we'll coin certain terms like IDSS, VP, and expressions for ID, etc. In last lecture, we studied that the structure of JFET is such that we have an N channel connected to drain and source terminals from its top and bottom, and we have two P type materials. They are connected together and collectively form the gate terminal. In last lecture, we applied VGS is equal to 0 volt at the gate. The voltage of gate with respect to source is 0 volts, and we varied VDS from 0 to a maximum value. And we study that as we increase the magnitude of VDS, the amount of reverse bias increases, and we have a non-uniform distribution of this depletion layer. This depletion layer, the width is non-uniform because the lower side, that is the source, is at a lower voltage compared to drain, the upper side. The voltage here is greater than the voltage here. So the amount of reverse bias should be different from top to bottom. That is why we have this non-uniform distribution of depletion layer. As VDS increases, this amount, the width of depletion region increases, and at a certain value of VDS, these two merge together. And then after that, we have a constant current flowing ID, the maximum current flowing. If we have VGS is equal to 0 volt, the characteristics are this. We have plotted VDS, ID versus VDS. As we increase VDS, the current ID increases up to a certain point here. This region is called ohmic region. Why ohmic? Because with the increase of VDS, ID keeps on increasing. After that, we have this saturation region when ID does not increase with increasing VDS. This region is saturation region. But we have other options. Before we go to other options, the current, the max current, or the current where the characteristic enter from ohmic region to saturation region, we give it a special name to this current. We call it IDSS. And any ID can be described in terms of this current. If we draw a perpendicular line from this point on x-axis describing VDS, we intersect at a voltage, we call it VP, pinch off voltage. So we have two terms, VP and IDSS, which are very important to calculate ID, right? But we have other options for VGS. We can have a negative VGS. For example, we can have a VGS that is negative 1 volt. If it is the case, what are the characteristics? If it is already negative and we start increasing VDS right from 0 once again, that we did for the case when VGS was 0, we'll get a similar characteristics. But at the initial point, the PN junctions here are more reverse biased because we already have, when VDS is 0, we already have a reverse bias of -1 volts. This means the saturation region will come earlier. So for VGS is equal to negative 1 volt, this will be the characteristics. This will be the characteristic between VDS and ID. Right. For a more negative voltage, VGS is equal to negative 2 volts, for example. We'll have another lower characteristics whose saturation value of ID is smaller. If we keep on decreasing VGS, we'll reach to a point where ID is 0. We call it VP. We'll reach to a point. In some books, we call it VGS off. So for VGS, maybe for VGS is equal to negative 5 volts, for example, there is no ID and we call it VP or VGS off. We have drawn another characteristics to the left of these characteristics. Here we have the same y-axis ID. The y-axis is the same. But on the x-axis, instead of VDS, we have plotted VGS, V gate to source. As we increase the magnitude of this VGS, we make it more and more negative, we come to a point where ID is decreased to 0. ID keeps on decreasing as we increase the magnitude of VS, we make it more and more negative, unless we reach to a point equal to VP, ID is 0. Mathematically, a good non-linear approximation for this behavior is represented by this simple expression. ID is IDSS, where IDSS is the saturation point current when VGS is equal to 0 volts times 1 minus VGS, the gate to source voltage applied, divided by VP. VP is the VGS where ID is equal to 0. So these characteristics or these facts can be verified by this expression too. If we put VGS in this expression, if we put VGS is equal to 0 volts, that would give us ID is equal to IDSS 1 minus 0 over something is 0 squared. So if we have VGS is equal to 0 volt, we get ID is equal to IDSS. Right? This is the same that we obtained graphically. And then if we put VGS is equal to VP in case 2, if we put VGS is equal to VP, ID becomes IDSS times 1 minus VGS and VP are the same, so we have 1 over 1 gives us a 1, so 1 minus 1 is 0, so we have ID is equal to 0. In many cases, we have to, we have to bias our transistor in the middle of the ohmic region. In the middle of the ohmic region, where we have this is ID versus VDS. This point gives us IDSS, and we are required to bias it for ID is equal to IDSS over 2. What is the amount of VGS here? In other words, we can draw it such a way to draw the characteristics, these characteristics, where we have this IDSS, ID, and mostly we are required devices here. So here we have negative VGS. So what would be the value of VGS if we have to bias the FET so that ID is IDSS over 2? We once again have to take help from the same expression that we wrote before. IDSS by VGS over VP squared. So we have to bias it at a point where ID is equal to IDSS by 2. So let's put ID is equal to IDSS by 2. So this IDSS cancels with this, and we have 1 minus VGS over VP is equal to 1 over 2 square. Taking square root on both sides gives us a VGS that is approximately 0.3 times VP. So in our coming lectures, we'll be studying more about DC biasing of FETs, and then we'll move to FET based small signal amplifiers. Thank you.